Hello and welcome to this video of the Arcade Hack series. This time we will make a special journey with hacking the arcade version of Final Fight. As usually, I run Mame with the bug and cheat argument, so I'll be able to write into ROM code and modify game behavior. At the end of this tutorial, you'll be able to create your own version of Final Fight Arcade. Object, enemies, game order sequence. It's all on your hands now. Area and stage values are stored as byte-size at this memory location. The value of the area changes with the current scenario: slam, subway, bonus scenes, and so on. Stages are the sub-level of the area. For instance, slam has 3 stages, subway 4 stages, bay area has just one. And remember that on computer programming, values often start from index 0. On slam stage 2, we see the stage value is increased, while the area is still 0. Here we are at the slam last stage. Value is now 2. Okay, let's skip through the next area. This is the first stage of subway. Notice the stage value resets to 0, while area is now 1. Now, let's say we want to play areas in a different order. We start play from subway, and after that we go to the slam area. Then we proceed with the original sequence. In order to start from a different area, we have to modify the first instruction. Here, it's the original area sequence. By modifying the content of this address, we change the order we play scenario during game. Let's do this. First, we replace the original instruction with setting value 1 on the area memory address. We can see the new instruction on the disassembler tool window. Next step is to replace the original value 1 with 0 on the area sequence address, so that we pass to the slam level instead of repeating the subway area. Let's see what happens now. Okay, we started from the subway area as expected. I'll use an available cheat in order to immediately pass the current stage and see the results quickly. Seems like it works. Remember that after passing this area, game will continue from the bonus car stage. Another important variable is the area position value. There are two available values, one for horizontal and one for vertical position. Both are word size, so a single value takes 2 bytes. The area position restarts from 0 when entering a new area. On some stages, like Industrial or Bay Area, we see the vertical position changing during the gameplay progress. On such levels, enemies are engaged according to the vertical position. Now we can start talking about the mapping of the stage data. There are two main addresses whose content is used for populating a stage of enemies and objects. For simplicity, we'll call this kind of data as such. Stage map and enemy map. Here's an overview of the stage map data content. Each entry is composed by initial position, character or object type information. First word entry defines when an object is loaded into memory. When current position reaches this value, the object is loaded into RAM. This marked couple of words defines the object's initial position. These bytes define the object type. If the first byte starts with 2 or 4, it's an enemy character. Otherwise, it's an object or weapon. The function of these marked bytes changes according to the type of object which is related to. When the last byte is set, it is enabled only on 2 players mode. That's the case of the barrel on Slam Stage 3, which is shown only when playing on cooperative mode. The following slides show the mapping code related to the enemies. Bosses area, objects, and stuff that pop up from breakable objects. In order to prove what we have explained so far, we'll change the first enemy we meet at Slam Stage, Red, with someone else. We can change the initial pose value and see what happened. That's it about the stage map. We'll be back later for it with doing other experiments, so don't worry. Let's turn to the enemy map data now. Compared to the previous stage map, enemy map data contains only information related to the stage enemies. But, unlike the stage map, into this content we define enemies who block us until we get rid of them. Therefore, if we want to proceed forward the stage, we need to kick their ass up. Enemy map data is composed by a header and several entries. The header part contains general information, while a single entry defines information for the related enemy. First word defines the position where we stop in the stage waiting for the enemy's wave. Second word is a timer value. When the value reaches 0, we can proceed despite enemies are still alive. This value represents the number of enemies required to beat in order to move forward. This is the address of the next enemy map address. Last, this is another timer value. It's basically the delay the enemy spawn starting from the last entry. An entry is composed by the enemy's initial position, the enemy character, and delay value before the enemy spawn on the screen, as we already seen previously. Unfortunately, as for this video, there is other data I still have no idea what it's for. Now, like we did for the stage map, we are gonna modify some parameters on the enemy map as well. As you may notice, the enemy wave comes early than expected because I changed the first value of the header. I have also changed enemies' positions and characters. You can see we are already facing Andorre. Finally, I've shortened the expiration time value so we can proceed on the next stage without beating all enemies. Player 1 and Player 2 relative data is located on a defined position in memory. Enemies are dynamically relocated on specified slot of memory. The first enemy we meet will be always located at a specific address. Later, things change according to the spare slot available. This is a snapshot of some available slots dedicated for the enemies. Each data takes a size of hex C0 bytes. Other objects type, like trash bin or barrel, take other slots in RAM. Boss data is always located at a predefined address. On the ordinary gameplay, we always handle one boss at once. Luckily, the system is enough clever to allocate spare memory in case we map more bosses on the screen. When entering the final stage of the area, we see the memory location reserved for boss fill its content with some values. Unlike ordinary enemies, most bosses are not mapped on any stage or enemy map. That's because they spawn only when meeting certain criteria. In most of the cases, it's about reaching a specific stage position. The only exception is EDE, who can be actually mapped and played everywhere. However, our scope is to remove these conditions, so we can meet them, Stardom, Rolento, and any other boss at any stage. However, there are some cases that several modifications need to be applied. Then, for instance, at some point of the fight, call for support. Therefore, we also need to modify the involved instructions. If you somehow already watched my hack on the first two Double Dragon series, you remember that I read the bytecode from the iTouch manual and directly write into the ROM. I'm not doing the same for the CPU 68000 because it's a much more complex CPU. Having the need for an assembler, I eventually switched to another software named EC68000. Despite it's probably discontinued, it's still a valuable product. It also features to show the output in machine language and allows to easily create binaries. Unfortunately, on CPU1 ROM, bytes are word swapped. Therefore, I had to use a Unix command to swap the byte content output to another file. And the results are out there. By using the Mame debug console, I can easily load my custom binaries. This is Sodom attacking me at Slam stage. You may notice the colors are not quite good, but don't worry. We'll fix that soon. Before talking about palette and colors, I want to show you how another hack on the Sodom stage. This is the routine in which the stage map address is extracted. Take a note of this address, we'll go into this soon. This is the address of the Subway 4 stage map. These marked values are the distance from the base address we take note before. If we add one of these values to the base location, we get the final address of the stage map. On the right, we see all the map locations for each stage. This is the new address where we are going to build the content of our custom map. Not bad, huh? Once I learned how to place bosses and enemies out of their ordinary area, I faced on certain cases some palette issues. In the same way we previously saw Sodom with odd colors, we can feel the same sensation having them on the subway area. Same condition applies when you map certain variations of the Andoris families. It appears only Andore and Andore Jr. are out front is glitched. So let's talk about how to fix this issue. We'll have a quick look on CPS1 and registers. This is the CPS-A register list. At this content, there is the address where the graphic instructions are written. Consider that ZFX RAM begins at location X 100,000. By scrolling down the registers, we see another interesting location pointer. This is the location where all palette information of OBJ and scroll objects are stored. The OBJ type is a graphics entity similar to a sprite composed by n tiles. Such tiles are chunks of 1 pixel with position and attributes attached. One of these attributes is the palette ID. A single tile can use up to 32 palettes available. This means we can have 0 to x1f value. Each palette is composed by 16 colors. Each color item is a word size and can display up to 65,536 values. The index 0 of the CPSA register content contains the OBJ base address. We can update the real location by shifting this value by 8. Therefore, we can understand graphic tiles instruction starts from location hex 900,000. This is a single tile entry with position X and Y, tile ID and palette ID. All these tiles ensemble compose the guy frame animation. We can see that such tiles use all the same palette ID, which is 0. At index A of CPSA register, there is the palette base address. Since Guy used the palette ID 0, we can move this address and see how the palette is done by looking the first 32 bytes. As a proof that things work like we previously explained, I'll paint Guy with black. This time I'll give him a blue carrot edge. For doing that, it is enough for some colors switching the red with blue value. Let's face them now and see which palette is used for him. These are the tiles that compose them. As we can see, them use the last palette ID available, which is hex 1f. All bosses always use the same palette ID, which changes from area to area. This is the reason why we will see wrong colors if we place them on a different area. Again, in order to prove we are on the right way, I'm going to modify values contained on palette ID 1f and paint the boss of all black. Looks like the Predator now. This routine I discovered while debugging helped me to easily understand the palette ID used by the objects on the screen. It was enough to place a breakpoint at the routine start and see what happened when the program counter reached the jump instruction. At this point, there are two registers mainly involved. A0, which contains the object in memory that is currently processing. We know that this location is reserved for player 1. D6 register, which contains the palette ID that will be used for the character in A0. Again, we already know that on Guy is applet palette ID 0. Let's go forward until the program counter reaches the breakpoint again. This time we can see on A0 there is a location reserved for enemy data. This is clearly bred, as it's the only enemy engaged at the moment. Again, from D6 register we know the palette ID used for it, the hex value 0E. This is the palette list used for each character. For ground objects, weapons and breakable objects. This is a rapid overview of the palette fixed code I wrote. I'm not going too deep into this. I just want to show you the strategy I adopted to fix the enemy's callouts. I have basically modified the routine we earlier talked. And before applying my custom instructions, I do some test assurance on the memory, so I'm sure that the current processed enemy is a boss character that is out of its area. Once all these checks pass, I override the expect palette value with the one that I have wisely choose. And this is the topic I'm talking next. On this demonstration, we'll see how to map a boss out of his area. First, we load the boss scripts file from the prompt, using the commands I placed on my website. Each topic contains two scripts. One contains the new code to insert into spare ROM memory. The other one, with suffix mode, contains the modification on the existing ROM and the jump instructions to the new routines. Now we want to place them, the boss of a slave area, on the first subway stage. Up to this point is quite simple. We replaced Roxy with Demon using code 4 and 0. This is the palette ID that we'll use for Demon. Indeed, the idea is to take advantage of the unused palette in the stage, and by setting value hex 1D, when loading Demon, I make sure to copy his palette into the location reserved for palette ID 1D. Obviously, you have to take care that the chosen palette ID is not going to be later used on the stage. Otherwise, you'll mess up with colors of other object or character. You also need to know that palette is refreshed only when entering the next area. For example, if you dirty one palette that is going to be used on the next stage, you still find an issue with colors. For the convenience, I created a script that refreshes palette on every stage. This is another demonstration. I'm going to place Rolento into the west side ring stage. Again, we load the scripts from the debug prompt. This time, I replace Akitana with Rolento. And I assign the palette 1D for handling him. We have talked about the boss palette correction. For fixing Giant Andorre's palette, I used a similar approach. But this time I was not allowed to take the same bite I used from boss Dala. This is because the initial boss bite is actually used for normal enemies. So instead of using the bite reserved for the initial character's pose, I'll take this one. This bite location is actually used on the game, but I didn't understand this meaning. So, as a trade-off, I choose that position because the other bites are already taken and used for different game logic. That's all for now. If you are interested in reading some useful sources for CPS-1 system, I strongly suggest browsing this guide. Helped me a lot on learning some technical aspect of this system. Also, if you want to gather more details about the topic of this video, check my GitHub repository. Last but not least, if you want to support video like this, please put a like on it. Thank you and see you on next video.